Hello and welcome back to my YouTube channel. This is Cheyenne, and today I'm going to solve another deflection problem using the moment area theorems. So this question asks us to determine the deflection and rotations at various points for this beam, and we're using different stiffnesses for various parts of the beam. But of course, the main difference that we have for this problem and the other problem that we did is the hinge here. So we have a hinged problem here. And that changes just a little bit here and there, but in general, we're going to use like the same approach as we did for the other question. So it's going to be kind of a similar solution. So first step will be for us to find the reactions. So previously it was easier because we only had like one main part for the beam and that's it. But in this case, we have kind of two parts for the beam. So we have like a hinge here. So that kind of gives us the hint that, okay, well, here we have to kind of separate the beam because we have to know the forces for all parts of the beam. So what can we do? As we know, this hinge transfers shear but does not transfer moment. So of course here we will have automatically like two forces. But of course, since this is a beam and there is no horizontal force here, we can eliminate this horizontal force and we only have vertical. So there will be a vertical force on the left side and there will be another vertical force here on the right side. How can we do that? Well, we just kind of have to separate it like this, right? But this point and this point, they will both have like a force equal, but in the opposite direction, right? So what's going to happen? We're going to have like a by right here, and we're going to have another by right there, okay? So I'm going to draw this later. But, so if we start with this one, and by the way, this is arbitrary, completely arbitrary. So you can draw it upward, downward, doesn't matter. But when I look at the beam right here, I can see that this is kind of, if this is a reaction here, and you have a load here, and you have a load here, I can see that this has to go in this direction because this load is relatively large, right? Comparison to this one. So this has to resist it. But again, these are small details. You don't have to pay attention to those things. So it's fine. At the end of the day, if you get a negative value, that means just it was the opposite direction. So, don't worry about these small details, for now. So just assume a direction and that's it. And of course, how do we analyze a beam free body diagram? So we remove this kind of roller here, put a reaction here. Again, another arbitrary direction. Good to go. And then we move to the other one. Again, you see this by is going up. Why? Because this by is going down. So if you are drawing this one up, this one should be down. So just keep that in mind. At the end of the day, this point has a net force of 0. Okay? And then by, okay, so how do we analyze this one? Free body diagram again. So remove the fixed support there. What are the reactions there? Of course, a moment and a force there. And so what we can do is just analyze this one. Where do we start from? Well, as you can imagine, this one, how many unknowns do I have? 1, 2, 3. Can I solve this? No. But this one, I have 1 unknown, 2 unknowns. Very similar to the previous question that we did. So we have kind of 2 main equations and 2 unknowns. So we can solve this problem pretty easily. So what we can do, we can come here. And so we're not going to start from this one. We're going to start from this one. And very similar to what we did before, we're just going to kind of take the moment about various points. In this case, I'm going to start taking the moment about point D. In this case, you can take it about point B, doesn't really matter. And I'm just going to assume that counterclockwise is my positive sign convention there. And I start from the kind of right side here. So I have 20 times 4.5. And this going in the clockwise direction, so negative. And then dy, of course, does not create any moment because it's going through the point. Lever arm is 0. Then you move on, 10 kilonewton, 10 times 1.5, right? Again, distance from point D. And this is kind of creating, you see what kind of moment about point D, if this is like a hinge, or if this is like a kind of pin situation there. If you turn this like that, it goes in the counterclockwise direction, so positive. And this is by, again, going in the counterclockwise direction, by multiplied by 3 plus 1.5, which is 4.5, and that's it. And the summation of the moments, of course, is going to be equal to 0 because of equilibrium. So from here, you isolate for by and find by as positive 16.7, and positive here just suggests that the direction we assumed for by was correct. Now, in this case, if you kind of drew initially by upward, then you would get negative 16.7 from this calculation. And that would mean that the direction you assumed right here was just in the opposite direction. That's all. And in this case, after this, we can take, again, the summation of the moments again, or summation of the forces. Summation of the forces in this case is easier, so that's what I'm going to do. So again, start from the right side again, negative 20, there you go, plus dy, minus 10, minus by. Simple as that. Okay, and by, we already know that. And dy, you just isolate for dy there and find the value. Again, positive, that means that the direction we assumed was correct initially. So that's how you get these unknowns. Now, the good thing here is that we now know what this by value is. by is 16.7 going down. That means that by here is 16.7 going up. So now we can actually go ahead and solve this part of the b. So this one is 16.7. And what I can do, I can just take the summation of the moments about a point, or I can just take the summation of the forces about a point. I can start with either of them, so it doesn't matter in this case. I'm just going to take the moment about like a point here. In this case, I'm not assuming any directions because this is pretty simple. So as you see, if I take the moment about point A, what are the forces? This multiplied by the distance and the moment, because this one does not create any moment. It goes through the point. So I have two forces, this one and this one. As you see, they're kind of canceling each other. Okay, so the signs are correct as well, right? This one's going in this direction, this one's going in this direction. So I don't have to worry about the signs either. So what I can do, I can just say MA is equal to 16.7 times 3. Okay. Now, if this is confusing for you, you can just go ahead like do like this. It's the same thing. I mean, it doesn't really matter. In this case, I just didn't put a sign convention here because it's pretty obvious. And then we take the summation of the forces in the y direction. In this case, as you see, if by is 16.7 going up, then AY has to be 16.7 going down. It's pretty straightforward. And that's it. That's how you find all the forces. Now that we know all the forces, of course, we can go ahead and draw the shear force and bending moment diagram. But of course, as I mentioned before, never forget the signs and direction of forces. Okay. Some cases, for example, especially here, I see a lot of problems where like people find this by value here, and let's say they find it negative 16.7, right, or something like that, and they forget to change the sign here, and this also kind of remains up, for example. Okay, for example, if this was negative 16.7. So keep that in mind. If this is negative 16.7, first switch it here and then come to here and, kind of make it opposite to this one. You know what I mean? So just keep that in mind. Like, these small mistakes can happen very easily. Now in this step, we can draw the shear force and bending moment diagrams. How can we do that? Well, like we did before, so the shear force diagram. And as I mentioned before, again, for the moment area theorem questions, we only need the moment diagram. So if you can draw the bending moment diagram kind of directly, absolutely go ahead and do it. But for especially moment area theorem questions, we don't really have like complicated forces, right? That's the usefulness of moment area theorems. Otherwise, moment area theorem is not really convenient for us to use. But that's why most of the questions that you see will have concentrated forces like this. So drawing the shear force diagram also is not really a big deal. It shouldn't take that much time. So that's why I do it here. But for more complicated problems, absolutely, I would say forget about the shear force diagram. Just go to the moment diagram directly. So how do I draw the shear force diagram? Well, I have 16.7 here going down. There you go. So going 16.7, so negative 16.7, then you continue. Remember, here you have a force, but from the left, for example, it was going up. From the right, it's going down. And both the same magnitude. So do I have to include it? Not really, because, so it's going to continue, right? But here at this point B, there's no change. Because it's going up, it's going down. And that's what Hinge does, really. Like, it's, it doesn't add it. It's not a reaction or anything. It's not a force. It's just like a transfer between these two parts of the beam. That's all. So there's no change in shear here. And you can even think about it like there's a force here going up, force here going down. So you can say, okay, going up and then immediately going down again. So there's no change in shear force at all there. So just whenever you see a hinge, just continue it like that. Unless there is a force on the hinge itself. So if there is a force on the hinge, then the situation is different. Okay, that's another scenario. So in this case, we continue again at point C. You go 10 down. There you go. So 16.7 minus 10. That's negative 26.7. And then you continue until D. And at point D, you have 46.7 going up. So you just continue going up like that. Plus 20 there. And then you continue at the end. Minus 20, you get to 0. And when we start from 0 and get to 0, that means that we did our shear force diagram correctly. Well, actually, to say it better, that is an indication that we did our shear force diagram correctly. That doesn't exactly mean that we did it correctly, but yeah, it's just a very good indication for sure. So that's how we do our shear force diagram. As you see, it doesn't really take that much time. So I was just, for sure, you can do that. And now at this stage, we can go ahead and draw the bending moment diagram. So here, we'll start from here, but as you see, right at the start, we have a 50 kilonewton meter moment that is going in the clockwise direction. As you remember, clockwise was a jump. So you jump 50 kilonewton meters. There you go. That's positive 50. And now I go to my shear force diagram. The area under the shear force diagram is what I'm looking for. So the area under shear force diagram I have from, you can measure it honestly from here to here or from here to here. At the hinge, I must have a zero moment. And automatically I will, right? So I would say it doesn't really matter if you kind of go from here to here or go from here to here directly, right? I can go from here to here honestly initially. So 16.7 times 3, that's 50, right? So it's like positive 50 minus 50. It gets to 0. Perfect, because that's what I want, right? So it goes to 50 right there, right? Again, this positive 50 that I have, area under the shear diagram is negative 16.7 times 3. So here, that's negative 50. 50 minus 50, that's 0. Then you continue this, another 50 there. So we go to negative 50 there, right? Because it's 16.7 times 3. And then at this point, I have another area, 26.7 times 1.5. It's negative again, so just go down a little more, negative 90 there. And then at this point, I have 20 times 4.5. It's a positive value, so just positive minus. This value actually just happens to be 90 as well. So this is your moment diagram. So again, nothing fancy, exactly like the things that we did before. Again, if you like to kind of learn more about moment diagrams and shear force diagrams, you can check the previous videos I did for shear force and many moment diagrams, and those will be really helpful in kind of solving this problem as well. So now that we have our shear force and many moment diagrams, we can go ahead and find out what our M over EI diagram is, right? And that's basically what we want for moment area theorem questions. So in this case, we're going to draw the M over EI diagram. Again, very similar to the previous question. So we have this part, but the only trick is that this part AB has a different stiffness and part BCDE has a different stiffness as well. So AB has a stiffness of kind of EI, and this part has a stiffness of 2EI. How do I do that? Well, I have to identify this, that, okay, this part is different, right? So what I'm going to do, I'm going to kind of copy and paste this. So see, it's like that, right? And this one just, you say 50 over EI. Remember, it's an M over EI diagram. So you're effectively just dividing your moment diagram by EI, okay? So 50 over EI right there. And this part, again, not much of a difference right there. But whatever you see here, you just have to divide by 2EI. So since the EI here is 2EI, so negative 50 over 2EI, negative 90 over 2EI. And simple as that, you just draw this part. So this is 0, good. Negative 50 over 2, negative 25. Negative 90 over 2, that is negative 45. And just continue to 0. Simple as that. That's our M over EI diagram. Okay. So for moment area theorems, doesn't matter how you get to it, right? But at the end of the day, we just want the M over EI diagram. You want to draw the moment diagram directly? Absolutely, go ahead. So at the end of the day, we just need this to start our question. And now that we have our moment diagram, we can actually draw the elastic curve as well based on the moment diagram. As you know, the elastic curve actually helps us a lot in the moment area theorem questions, because at the end of the day, moment area theorems are basically just a graphical method, right, that we have. So it's going to be very essential for us really to kind of know the elastic curve of the beam that we have. So how can we do that? As I mentioned before, again, the moment diagram here is going to be very, very crucial in solving, in kind of like drawing the bending moment diagram. Of course, you can imagine, so as you're solving more and more questions about like the elastic curve, how it looks and so forth, after a while, you just kind of get a hang of it, right? It's just, you just see, okay, maybe I know what it looks like. This force is larger, blah, 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 and so forth. But if you think, okay, you know what, you want to say, I don't want to complicate stuff for myself. I just want to be safe. I would say the moment diagram is the best kind of approach to start that part. How can we do that? Well, here, the positive moment here indicates it's concave up. The negative moment here mentions that it's concave down. So very important indication that this part of the beam is going to have a concavity like this. This part of the beam is going to have a concavity like this. Okay. Now, how can I do that? Well, very important thing you can pay attention to here is that this 20 kilonewton, first of all, it's much larger than 10 kilonewton, double. And also we have a large lever arm here about this point. So it's going to bend it so much that it's going to actually like continue this way, like, well, actually, let me show it. So on the left side, of course, it just has to be like this, the hinge. So when you if you can imagine a ruler, you push it down and you just neglect this one for now because this is not much, right? Neglect this one for now, but you push so much here, it's just going to deflect like this. And then since it's a hinge, it's just going to deflect like that, okay? Why is it like this? Well, I would say it's more visual. I would say if you want to kind of experiment that, you can put like two kind of metal or flexible rulers beside each other, connect the ends of them, which has like a circle in them, with a paper clip, and put an eraser below this, okay? And forget about this one. Push this one down, okay? Push this one down, fix it with your other hand. So kind of grab it with your other hand right there, fixed, and pull it down. You're gonna see it's gonna deflect something like this. And then here, since this ruler is kind of separate from this one, right? It's a separate kind of body by itself, right? It's not gonna continue. This fixed support doesn't let this go up, okay? Because of the compatibility of deformations here and like so as you know, the fixed support, this just has to be zero slope and zero deflection. This has to go like that. Okay, if it wasn't like that, then it will be different. If it was a pin, it would be a different situation. But since it's a fixed support, that's just what's going to happen. So elastic curves, again, are a very visual kind of way to solve a problem, and just have to do it again and again and again to kind of get a hang of it. So yeah. So in this case, how do I draw this part of it? Well, in this case, this is how it's going to look like. Okay. So this one is pretty straightforward. So because there's not many ways you can actually draw this. So it's going to go like that, or it's going to go like this. Okay, but before that, actually, let me talk about this. So again, as you can imagine, I'm pushing it down, goes like that, and here it has to go back like this. Okay, it can't go like this because it goes like this, right? You might say, okay, why is it not going like this? Well, because then there's a concavity change. It's concave up, and then this is concave. It has to go concave, like it has to be concave up here, right? If it's concave up, then there's a point of curvature here. If it, in other words, if this continues, at some point between A and B, it has to change curvature. Where is that point between A and B? Is there any point of zero moment? Because that's what indicates for us that's the point of curvature. There is none. So the whole thing is that from A to B, the curvature is up. Okay, and since this is fixed, it's just gonna go like that. Simple as that. Okay, and now for this part is pretty obvious. Of course, you're pushing it down, but for this part, what you would say, okay, of course it's concave down still, so it has to go like this. But you must say, okay, why is it not going like this? Why not like this? Valid point. The problem here is that the force is large, the lever arm is large, so it's pushing it so much that it cannot go like that. Okay. If this kind of support that you see here was here, or like maybe closer to the end, or this force was much smaller, then in that case you would be right. Yeah, it would go like this with the with the dash line. But that's not what we have. Okay, so again, these are small details. It's not gonna probably change like the problem exactly like that much, right? And at the end of the day, even if you draw the elastic curve differently than what I've done here, when you're solving the problem and you're using the second theorem, you're gonna see that wait a minute, there is a problem here. When you see like there's a contrast, that means that we made a mistake in drawing the elastic curve there. So there are so many kind of indications of how, if we drew the elastic curve correctly, and I would suggest the best kind of way to kind of conquer all of these solutions is to kind of do them again and again and again, and do them with various types of problems. In this video, I'm not going to particularly talk about the momentary theorems themselves and what they are and where they came from and so forth. So for that, I have another video, Momentary Theorems 1. So for sure, I would say before continuing this part, continuing after this, just watch that one if you want to kind of refresh your memory about what the theorems are and how we can use them in different kind of scenarios. But we're going to basically just apply those theories here. In this case, it's just more about problem solving for this part. For this question, we're going to start with the left side of the beam. Why do we do that? Well, because in this case, I have a fixed support. Anytime you have a fixed support, you know that that gives you a lot of information about the deflection and rotation. We know that deflection is 0 at this point and rotation is 0 at this point. So effectively, I can use actually both the theorems to kind of find information about any other points here for part A, B, right? And as you can see here, for this part, if I don't know the rotation here, if I don't know the deflection here, I'm probably not going to be able to solve the other parts of this beam. So I can't really start from this part. So the only thing I know here is just the deflection here is 0. That's all I know. And so it will be very difficult to solve the right part of the beam without knowing the deflection and rotation here. Kind of the matching condition, if you will, here. Like that for deflection. For rotation, of course, it's just another value right there. Now, the thing here is we have to kind of come up with an initial point if you're trying to find the slopes, again, for any of these parts of the beams. And remember that for a hinged problem, effectively, we're going to kind of treat them separately, right? Similarity-wise, I would say it's very similar to the deflection method of integration question that we had. If you remember, we had, for example, for the cantilever part, we would say, we have a matching condition, and we would go find the rotation at the pin from the right side and equal to the left side. That's kind of what we're going to do here. We're going to find the deflection here, because without the deflection here, we're not going to be able to solve part B, C, D, E of this problem. But more on that later. So the point here is that we have to come up with an initial point because we know that slopes can be found. If I know the rotation for one initial point, I can just go ahead and solve the rotations for the other points using the first theorem that I have. Well, this question is pretty straightforward for part AB because I already know that rotation at point A is 0. So, but in general, for hinged problems, virtually we're splitting the two parts, as I mentioned before, and the deflection at build. So we have to find out what the deflection and rotations are at point B, and then go ahead, use the deflection at B as a compatibility situation, or compatibility condition, kind of a matching condition, if you will, to solve this part. So it kind of becomes another problem, this one, by itself, with some additional information about the deflection at B. It seems a little bit complicated at first, but trust me, it's just, you just have to know where to start. And when you see a hinged problem, start with the easy side. If it's a fixed support, start with the fixed support, okay? Because that's where you will get the information you need for the other parts. Even if it's not asking, even if the only question is find the deflection at E, you will still need to start from this point, this part of the beam, and find out what the deflection is at point B. And how do we find that deflection value? Well, as you can imagine, we want TB with respect to A. So you draw the vertical deviation at B, you see where the deviation is, okay, from a tangent from A. So tangent is, of course, just horizontal because this, as we know, it's a fixed support, horizontal slope there. And the deviation from the slope that you see to the deflected curve. Simple as that. And, well, look at that. Happens to be exactly the value for deflection that we're looking for. So TB with respect to A is actually exactly equal to delta B. So let's see how we can solve that. So let's start easy. Let's try first and find out what theta B left is, right? How can I do that? Well, I know my theta at A. It's 0. And as I mentioned before in the other video, you always go from left to right for rotation. So you would say theta A plus theta B with respect to A is equal to theta B. Simple as that, okay? So this is the theta B left that I'm looking for. So I'm just kind of drawing like a tangent here, just to find out what the slope is. And this is the relationship that we have talked about before. Okay. Now the thing is, here I do know what my theta A value is. It is 0. So the only thing I need to know in this case is just this theta B with respect to A. I know theta is 0, and theta B with respect to A, according to theorem, is the integration from A to B of the M over EI diagram, effectively the area under the M over EI diagram between A and B. And from there, it's just this hatched area. You find out what the area is here. It's just a triangle, 50 over EI times 3 divided by 2. That's 75 over EI. And positive, what does that indicate? Counterclockwise. Okay, simple as that. So since this is 0, this is positive, this becomes positive. So theta B will exactly be just 75 over EI counterclockwise. Simple as that. Again, remember, for rotation, positive counterclockwise, negative clockwise. Okay? So simple as that, we find out what our theta B left is. Remember that I'm mentioning theta B left. Theta B right will be a different value, and we're going to find that out later in the next part of the question. Now, we found out what theta B left was, but as we said, the main thing we really need here is this delta B, okay, with this deflection at B. How can I find that? Well, in this case, I know, as we talked about before, this is TB with respect to A, right? So this is TB with respect to A. Why is that again? Because again, you draw a slope from A, deviation is measured at B. Slope from A, deviation measured at B. So, in other words, we say that delta B is equal to TB with respect to A, of course. And according to the second theorem, that's just the moment of this area about point B, right? About point B, right there, okay? So that is the point. And it's like, again, a force, right? It's like this is a force, lever arm. So if there's a triangular load, right? So it's like the area is like 50 over EI times 3, right? If you imagine like this is like a distributed triangular load. 50 over EI times 3 divided by 2, so that's the area. The lever arm will be a third from the edge, or 2/3 from the kind of pointy end that you see. So 2/3 of 3 will be 2. So it will be the area that I have here, so the same 75 over EI, multiplied by 2. Okay? Simple as that. You see? Area multiplied by the lever arm. Okay? And again, another question might be, how do you decide that this is about point B? It's always about the first letter that you see here. You take the moment of the areas involved. So in this case, since we're doing B with respect to A, the area from A to B that you have, just take the moment about the first letter. Simple as that. Okay? And that will be your value. Remember again that, so this mistake happens a lot, so that's why I keep bringing it up, because so in this is a positive value, because this was positive, everything's positive. This positive and negative here that you see, right, if you might see, has nothing to do with the sign of the deflection value. It only indicates that if the point was above or below the tangent. Since this is positive, that means that the point was above the tangent. Okay, so this is the tangent, this is the point on the curve, the deflected curve. Simple as that. That's what positive indicates. And this is where you can actually confirm your diagram as well. So let's say you drew it another way. You draw it like this, and you find the value positive. That means that, oh, you probably made a mistake in the elastic curve. Okay, so that's again your confirmation for the elastic curve as well. Everything should kind of match. That's all. So since this is 150 over EI, and effectively we know that TB with respect to A is equal to delta B. That's it. So delta B is just 150 over EI. And as we see from the diagram, it's going up. Remember, when you see positive here, when you see negative here, that doesn't tell you much about the sign of the delta. For the sign of the delta, you just look at the diagram here, the elastic curve. That's all. Okay? So that's how we find the rotations and deflection at point B from the left side of this B. Next, we're going to find what theta D is. You might say, wait a minute, but theta B right makes more sense, doesn't it? So I did like theta B left. You did deflection at B, just, go from left to right, like theta B right. Well, the thing is we can't actually find theta B right from the information that we currently have directly. What we can do is actually find out what theta D is. And as you know, for each part of the B, if we know any rotation, we can find the rotation at any other points that we have using the M over EI diagram, okay, using the first theorem. But as you see, for part BCDE, we don't have, so we have it be from the left, we have rotation from the left, we don't have it from the right or anything, or we haven't, we don't have any of these values. So I can't actually find out what the rotation is because I don't know any of these points. But what I can do though, I can actually find out what one of these rotations are using the second theorem. So this part is going to be very similar to what we did initially. We found an initial point in the previous video for one of the supports. Okay, very similar to that. How can I do that? Well, this is where the deflection that I found comes into play. Why? This is theta d. Okay, this is theta d. As you see, like the theta is facing the hinge, so that's the theta that you want to find, right? And in this case, if I draw a tangent here, okay, so which would effectively, just mean, okay, so if I draw a tangent, this would be the angle in this triangle right there, right? And what would be this value from here to here? That would be just TB with respect to D, right? TB with respect to D, because I'm drawing the tangent from D and I'm measuring the deviation from the, kind of deflected curve from B. Okay, so that's TB with respect to D, but wait a minute. I know this. This is the deflection at B that I already found from the left side of the beam. So that means that for this triangle, so let's go ahead. So here, I have this, and I can find, so I have this, I can figure this one out from the second theorem that I have. And that means that if I add these two together, I know this side of this triangle. And wait a minute, since this is a triangle, I can figure out what theta d value is right there. And as we know, if I know theta d, I can find out the rotations at any point. You want a rotation at B right, rotation at E, any point, right? I can find the rotation at any point that I want. So what I can do, I can write a relationship right there. I can say theta d actually is just TB with respect to D plus delta B. So this side, okay, it's just a tangent basically, divided by the length of BD, which is just 4.5. So this length divided by 4.5 is my answer for theta. And remember that, again, I didn't write tangent because tangent and like the x functions are equivalent in the vicinity of 0. So basically the idea here is I know delta B, I know the length BD. The only thing I need to find is just TB with respect to D using the second theorem. So I'm just going to go to my diagram right there, right? So delta B is known, of course. This will be the theorem, second momentary theorem that I have. So it'll be just the moment of areas about which point? The first letter, point B. So about point B, these are the areas of concern, 1, 2, 3. Why do I separate them like that? Because it's easier to find the centroid for a triangle and a kind of rectangle separately rather than just finding it for a whole trapezoid and it's just more difficult, that's all. So in this case, what I'm going to do, I'm going to go ahead one by one, separate these areas. So area of this multiplied by the distance. Area of this multiplied by distance, area of this multiplied by the distance. So the distances are here defined, the lever arms basically for each of these areas. And so for the first one, for area 1, area of it is like negative 25 over EI multiplied by 3 divided by 2, that is the area, multiplied by the lever arm. The lever arm is of course a third from the edge or 2/3 from the pointy edge. So 2/3 from the pointy edge is 2/3 times 3, that is 2, right? There you go. And remember, put the negative there, okay, because the whole area is negative. For area 2, it is just the area again. So negative 25 over EI multiplied by 1.5 right there, right? Multiplied by the lever arm, which is 1.5 over 2 plus 3. It's a rectangle. The centroid is in the middle. There you go. And for the other triangle, it's negative 20, because that's the magnitude of the triangle right there. Negative 20 over EI times 1.5 over 2 times 2/3 that you have. So 2/3 of measured, well, I would say, okay, so 2/3 of this 1.5, you see here, plus 3. Okay, so 3 is here. And you have the 2/3 of this 1.5 right there. It's just a lever arm. So this is from the centroid to the point B that we have there. So now all of these values together, you get this value. Again, remember, negative and positive here, it just indicates if the point is above or below. In this case, negative means that the point that you have is actually below the tangent. So where's the point? The point is here. This is the tangent. So the tangent is here. Point is here. Point is below the tangent. That's what negative indicates. Okay. So the only thing we wanted from here was the magnitude of TB with respect to D. We don't care about negative and positive when we put it back into the equation. So here, you're going to say TB with respect to D, you just put the value. Okay, remember, we're adding these like just algebraic. That's it. I mean, there's no negative and positive, right? Just absolute values. That's it. Okay, because we can see it, right? It's a triangle, and I want to add the magnitude of this to this. If there's negative, positive, doesn't matter. That's not what I'm looking for. Okay, so this value plus 150 over I, the deflection, divided by 4.5, you get this value, and that will be your rotation for point D. Okay. Now you might say, hold on a minute. Where did you get this clockwise? It's positive. Well, here the only thing we are trying to find for this only specific unique situation. Okay. Always yes. When you're trying to find rotation and deflection. Well, actually, let me say it like this. For rotations, if you're using the first theorem, absolutely yes. But if you're trying to find rotations with anything other than the first theorem, in this case we're using the second theorem, then in that case that rule doesn't apply. You just have to look at the elastic curve. At the end of the day, wherever you doubt any situation, just go to the elastic curve and take a look. This slope is a negative slope. Okay, this is positive, this is negative. Counterclockwise, clockwise. Or you can take a look at the beam. So here, this is the horizontal original shape. This is the curved. So as you can see how it's deflecting like that. That's what? That's clockwise. Simple as that. Okay. So many ways to kind of determine that. But the rule that I mentioned about like the first theorem does not apply here, right? Because this we're finding the rotation using the second theorem. Just keep it in mind. Seems like a lot of details, but if you just do the problem a couple of times, it's just gonna become muscle memory, I'd say. Okay. And now I can go ahead and find the rotations at any other point that I want. Okay, so in this case, I'm trying to find rotation B right now. Okay, because the question said, okay, find the rotations at B. So rotations at B. So from the left, I found it. Rotation at B. From the right side, I don't know it, but I can actually find it using the first theorem. It's pretty straightforward. So as we talked about before, if you're trying to find rotation using the first theorem, you always go from left to right. So theta B right plus theta D with respect to B will give you theta D. Simple as that. So I'm trying to find theta B, of course, in this case, so theta B right. So you just kind of draw a horizontal line here. That's the continuation of the curve. And that's theta B right, basically. And as you can see from here, it's actually clockwise. So it's going like that. But again, we'll see it again. In this case, since we're using the first theorem, we can actually just use the signs in the theorem itself. And so theta B would be right plus theta D with respect to B gives you theta D, again, moving always from left to right. Although I'm trying to find this point, I'm again moving from left to right. And here you just isolate for theta B right. So theta B right is just going to be theta D minus theta dB. Do I know theta D? Yes, I just found it. Do I know theta D with respect to B? Well, I can figure that from the first theorem. So theta D, I already know this. It's clockwise 94.583, or in this context, it's negative 94.583 over EI. Now for theta D with respect to B, it's just using the first theorem. So the area under the M over EI diagram between points B and D. So in this case, what can I do? These are the areas that I have, and I actually kind of found them before using the second theorem in the previous part. But again, I just have to write them again. So the area for the triangle, area of the rectangle, area of the triangle again. You just add them together. That's theta D with respect to B, which is just changing rotation from point B to D. And that is negative. Negative means what? Clockwise. So what you do, theta D, here is where it's important. So theta D is clockwise. So clockwise, you can just assume it's negative. So negative 94.583. For theta D with respect to B, oh, it's negative as well. So it's negative minus negative. Okay, so negative minus negative. Okay, so when you're substituting these values, whenever you're using the first theorem, always pay attention to the signs. If it's clockwise, you're gonna put negative. If it's counterclockwise, you're gonna put positive. Okay, that's all. And so when you do that, you're gonna get this value. And since it's negative, that means again that it is clockwise. Okay, so that's how you find the rotation for point B from the right side. Now we can just get the rotations kind of out of the way. Theta E, again, we can just use theta B, theta D. In this case, theta D is going to be much easier because I already know theta D, and this point is closer, so I have to calculate less areas. So theta D plus theta E with respect to D is going to give me theta E. Simple as that. Okay, so this is theta E that I'm looking for. And as you can see, it is clockwise again, right? See, horizontal, the slope going like that, clockwise. And so theta D is what we found before, this magnitude clockwise, or negative 94.583. Theta E with respect to D, I can find it from the first theorem. And from that, I can just add them together, find theta E. So theta E with respect to D, I just, again, go, since it's DE, I go between D and E. This is the area that I isolate. There you go. And this is the area I have to calculate. So negative 45 over EI, okay, times 4.5 divided by 2. Simple as that. That's the area I'm looking for. This is the value you get. And it's negative. That means that, of course, again, clockwise. The change is clockwise. So theta D is negative 94.583 because it's clockwise. Theta E with respect to D is, again, what I found negative. Just going to add them together. You get negative 195.833 for the rotation at point E. Since it's negative, that means it is clockwise as well. And lastly, we can figure out the deflection at point E. In this case, we can use the second theorem. Anytime you want to find a deflection, really, you just have to use the second theorem. And how can we do that? Well, in this case, I know that I have to kind of draw a deviation from some point to the other, right? I can use point B, I can use point D, doesn't matter. In this case, I'm just gonna use point D because it's like closer. So what I can say, deflection I'm looking for is this one, of course, delta E, right? But what I'm gonna do, I'm gonna draw a deflection, the slope, kind of the deviation from point D. I'm gonna measure it at E. Okay, so this delta E I'm looking for. But what I'm gonna do, I'm gonna kind of draw this slope here from point D and measure it at point E from the curve. So this value will be TE with respect to D, right? TE with respect to D. And this value will be psi. Now, what is this psi? Well, this is a triangle, okay? This is a triangle. And I do know the rotation at point D. So since I know the rotation at point D and I know this length, I can just multiply them together and from there I can get psi. So effectively from here, I know psi, right? I can calculate it easily. TE with respect to D, I can just use a second theorem to kind of find the value from the M over EI diagram. And so as you can imagine, if I kind of add these two values together, I'm going to get the delta E value that I'm looking for. So this is what I have, right? And by the way, you could do this with any other point, like you could do this with point B, okay? You can't do it with point A, okay? That doesn't work, okay? Because again, we're kind of virtually splitting these two parts of the beam, right? You can't use like the left part to solve the right part like that. Okay, you can use it as a compatibility to get any other values, but you can't use it directly. So you can use either point B, point C, point any other point that you want on the right side and draw a slope from there to figure out what the kind of T of any of that, like T of E with respect to any of those points, okay? In this case, I chose again. I would suggest always just go with the nearest point because you have to deal with lesser areas, right? Fewer areas, basically. You don't have to be as much. In this case, I have to only deal with one area here. Okay, in the second theorem. So psi, how can I find psi? Right, and this is the theta D, of course. So psi, I can find theta D multiplied by the length D. I know what my theta D value is. So that's my theta D, and it's 4.5. So the magnitude of psi from the distance from here to here is just this much. Good. So the only thing remaining for me is just to find TE with respect to D. How can I find that? Second theorem. So I'm going to go between points D and E. Just, you know, this hashed area is what I'm looking for. And of course, there will be a lever arm. So the distance will be measured from the centroid of this area to point E. Why is it point E again? The first letter. There you go. So we measure the kind of, it's like the moment of all these areas with respect to point E, or the first letter. And in this case, you just say, okay, the area is known, 45, negative 45 over EI, multiplied by 4.5, divided by 2, area of a triangle. There you go. Multiplied by the lever arm, which is 2/3 from the kind of pointy edge, right? Pointy end, kind of. So 2/3 of 4.5, that is 3. Okay, there you go. And from there, you get the TE with respect to D. Again, negative and positive doesn't really mean much. The only thing it means that the point that I have on the curve is actually below this tangent. Point is below the tangent. That's what negative means. If it's positive, that means that point is above the tangent. But of course, that's not the case. So That's what we get. So effectively, we now know the magnitude for this value and magnitude for this one. If we add them together, as you see here, I'm going to get my delta E. Okay, so I add them together. Magnitude-wise, I'm going to get this value. You might say, wait a minute, this is negative, this is positive. What does that mean? Well, again, as you see, magnitudes. This is a magnitude, this is a magnitude. This negative here means something else. If this is positive, again, it's just a magnitude I'm calculating. It has nothing to do with any of that. The only place that you really use the signs very consistently is the rotations when you're using the first theorem. That's all. Otherwise, you always have to look at the elastic curve itself and see what you're dealing with, okay? And so, yeah, that's it. So that's how you find your deflection at point E. And of course, I can see from the diagram that it's going down, right? So this is the initial point, it's going down, right? So that's why I just put a sign here going down, and that's it. If you have any questions about this video, please comment them down below and subscribe for more content about structural engineering problem solving. Until the next video, bye.